Okay, I want to talk about a dipole field. Now you can think about electric charges if you wish. You can't think about gravitational charges, which are inverse square charges, just like electrical charges, because there's nothing that we've observed that indicates that there's any such thing as a negative, well, actually a gravitational field is sort of a negative field, it's an attracting field. But there's no repelling gravitational field, at least at any scale we've ever been able to investigate. I say we, I've not investigated them, but I stand in awe of those who have. Okay, let's look at the field on this dotted circle due to the negative charge. Okay, the field is just an indication of the force exerted on a positive charge at a point. It's the force per unit of charge at that point. So if I have a point here, let's just say that my electric field excuse me, is represented by an arrow of this length. Attracted, the positive charge being attracted toward the negative charge. Not this positive charge, but some positive charge that we might want to put there. What we might call a positive test charge, which is the traditional terminology. Well, what's going to happen then to the same positive charge, some unit positive charge at this point? It's going to be attracted with the same force in the direction of the negative charge. So the vector is going to have equal length. So now I can sketch vectors at points around the circle. And I get a picture, pretty good visual representation of what's going to happen to charges at this distance from the negative charge. Now I can come up here to the positive charge and I can do the same thing, except that the charges are going to be, the positive charge on this circle would be repelled from this positive charge. So the vectors will be just as long as these if this circle has the same radius as this one. It'll be about this long. I'll put this point where it should be if that circle had come out as far as it should. Okay, well, maybe I got carried away with the length of some of these vectors up here, because this one is clearly significantly longer than this one. This one is maybe a little short. Just extend the point on it, make things look just a little better, but you get the idea. Okay? Now, the field due to the dipole at any point is going to be the sum of the field due to this charge and the field due to this charge. So let's draw a couple of circles about halfway between these charges, which is coincidentally on this part of the picture. Coincides with the tips of these vectors, but that's just a coincidence. I could have drawn it at any point, but that's just turned out to be about halfway. And I'll go same thing, I'll do the same thing here. Not perfectly drawn, but we get the idea. Okay. Well, assuming that these circles have double the radius of the original circle, which isn't quite so, but we could have pretended so, then the field at points along this circle and points along this circle will be 1/4 as great as the field that we drew here because of the inverse square relationship. So 1/4 of this length, let's see, we subdivide that in half, and then we divide that in half, we get a vector about this long. So these yellow vectors indicate the strength of the field and the direction due to the positive charge. And I'm going to draw purple vectors for the force due to the negative charge. Start down here. Again, these vectors have the same length as the ones I drew here, or they should. Now, let's see, this one's kind of in the way, but I'll kind of offset it a little bit. Okay, that should be of equal length. Didn't quite manage that. Okay, so there's a depiction of the two fields at about double the distance of the original. What we end up with at this point being equidistant between the two, is a field of twice the magnitude of either of these. These two vectors add to give us a vector of about this length. Now, I'm not going to draw the circles because they're going to significantly get in the way, but the distance from here to here is roughly twice the radius of the circle. Now, if you do the geometry, you'll find out that's not really true. You can figure out what it would be, but it really doesn't matter a whole lot. Okay, so if we go to twice this distance, the vectors are going to be 1/4 as long as they were here. The vectors due to the negative charge. So now I've got the vector that's due to the positive charge. Got essentially the electric field, or the field of the positive charge at this point. We superimpose that on the field of the negative charge, and we get a vector directly away from the negative charge that's only about 1/4 the length of this vector. Now that's actually more like half the length. Kind of exaggerated it. And if we put those two together, we have a vector that makes a slope of about 1/4 with the horizontal direction. And so wrapped up in getting 1/4 of the distance, that I drew the field vector from the negative charge as if it was a repulsive field. So let's fix that. Draw this thing again, about this long, and this short vector is supposed to be in the direction of the negative charge. A little hard to do that with chalk, no excuse. And we get a resultant vector here. Now I'm going to draw a little bigger picture of how that would actually likely look. Draw the picture over here. So we've got a vector representing a field with a positive charge, a vector 1/4 its length, which would be about this long, representing the attraction of the positive charge to the negative charge at this point. And we can do the parallelogram, or we could do a head to tail vector, but I don't want to risk it. A little hard to locate things accurately with the chalk. So here's our net field. So I'm going to use this orange chalk to indicate the next net field. I can do that at every point on the circle. I can do that at every point in space. The distance from here to here is the same, and then from here to here is supposed to be the same. So that at this point, this vector should be just a little longer. At this point, the strength of the field due to the negative charge is going to be, since this point is 3 times as far from this charge as it is from this charge, it's going to be 1/9 as great as the field due to the positive charge. So that I can draw a very minuscule vector here, 1/9 the length of this one. That's not going to be much at all. Okay. And I can kind of indicate this by a circle over here, or within a circle over here, where the picture is somewhat magnified. And this vector has 1/9 the length of this vector, so that the resultant vector, which I'll draw parallel, would offset a little bit. It's just a tiny bit shorter than this vector. Now we can go around the circle and see how these vectors interact. At this point, we would have a vector toward the positive charge, but it would be probably, instead of 1/16 as long here, around 1/25. That's not exact. You can work it out if you want to do all the geometry. We're going to have a very short vector here. Not quite as short as this one, but fairly close. That's going to tend to have the electric field being just a little bit, didn't draw it very well. It's going to be something like this. It's going to turn the field this way a little bit and shorten the vector a little bit. And I didn't draw it very well. It looks just about as long, but we get the idea. Okay. Along a horizontal line, and I do want to do that horizontal line. Before I do that, let me do a horizontal line here. Okay, along a horizontal line that bisects the segment between these two charges. We're going to have something a whole lot like this. Okay, at this point, we would have a vector fairly short, indicating repulsion of a positive charge from the positive charge, and another vector indicating repulsion of the negative charge, or the attraction of the positive charge toward the negative charge. When we put these two together, we get something like this. And as before, let's take a look at how this looks over here. Fortunately, that was a white chalk I dropped. I don't need it just yet. So I'm going to have a vector like this and a vector like this. Because of symmetries, the vectors will have equal length and they'll make the same direction, they'll make the same angle with the horizontal direction. I can sketch my parallelogram here to visualize where this vector is. So it's going to be straight down. Along this line then, the same thing's going to happen at every point, but the attraction is going to fall off quite rapidly. So we'd have a smaller field here and a very minuscule field here. Okay, the field's going to fall off quite rapidly. That should be enough to go on and sketch field lines. Okay, we don't have a complete picture, but we have enough intuition perhaps from these few points, from the approximating the field at these few points to see what's going to happen. So I'm going to do that in a separate video.